Okay, question number 2. So this is link state path routing. It is using Dijkstra's algorithm to figure out the state of a routing table. So part A is true or false. Link state packets are distributed across the entire network via a process called controlled flooding. This is true. Basically, each link state packet will go to the neighbor, and then the neighbor will forward it on to the rest of the network. So next up, complete the routing table to the right for router E. So E is our start point, and we're figuring out what the fastest path is going to be to get to every other node in the network. So we can start by going to F and seeing that F has a distance 1 from E. Going to D from E is probably going to be 4, but we'll have to check to make sure the circle route is not faster. And we'll do that once we get to C to see if C plus 1 is going to be any quicker to get there. We'll go to F and see that 1 plus 3 is going to be 4 for the total cost for A. And then going from A to B is going to be 5. And then at that point, B to C is going to be 8 if we do 5 plus 3. So 4 plus 1 is actually going to be faster. So C is also going to be 5. And we can pretty clearly see that, circling around to get back to D is not going to be any faster. So these are our weights for the network. We now know which directions we went for each path. From E to get to C, we went that way. And from E to get to B, we went that way. So our next hop for A is going to be F, because that's the direction we went to get to A. We went through F and then to A. And our total cost to get to A is 1 plus 3, so that's 4. To get to B from E, we went through F, A, B, and the total cost was 5. So we went to F first, total cost being 5. So we're just going to have the initial, or the next hop is either going to be F or D for all of these answers, because those are the only two directly connected to router E. Okay. Next up, C, we went through D to get there, and the total cost was 5. D, we went from E straight to D, so the next hop is, in fact, D, total cost of 4, because that was the length of the path. For E, we don't have a next hop or total cost because that's the node itself, so it's not going anywhere. To get to F, we just went straight to F, and the total cost was 1. Okay, so next up, we say a brand new router labeled Z is connected to the network. So I'm going to go ahead and put a Z in the middle here. Hello packets are exchanged, and router E receives the link state packet below. Add an entry for router Z to the routing table for router E below. So we have a couple more connections here. Z is connected to B with length 2. Z is connected to C with length 3. Z is connected to D with length 1. And F is connected to Z with length 1. Okay, so we want to add Z to this table. So we're going to add destination Z down here. The next hop, to get to Z, we could go through E, which is 4 plus 1. We could come up around here. That's definitely going to be slower. And we could go from E to F to Z, which is going to be a total cost of 2. That's going to be the smallest cost because the shortest link coming into Z is 1, and it's not directly connected to E. So there's no other way to get there faster. So we're going to go through F, and the total cost is going to be 2. Okay. Part D, true or false. With the addition of the new router to the network, more efficient paths to previous destination routers may be identified. You can probably just guess with this that because of the fact that Z is in the middle here, it's likely to add some new optimal routes. We can just spot check that E going to F going to Z is length 2. Going up to B is going to be 2 plus 2 is 4. So we're going to have a faster route to B. So it's going to be true. Next up, which of the following protocols is used by routers in intranet routing to determine network topology? So the keyword here is intranet, and then determine network topology. So BGP might be an answer if this was internet. HTTP is an application, so is FTP, DNS, and Samba. So those ones we can kind of cross out. BGP is internet, not intranet. And so then the only thing we're really left with is ARP or OSFP or OSPF. ARP is to identify things on a local network to determine what a MAC address is from an IP address. So learning the actual topology in the question here should be sort of a clue that it's OSPF, because we are looking at link state packet routing. Hello packets and link state packets are both part of OSPF. Which of the following commands can be used to scan a network and determine what hosts are active? So this is a question from the lab exercises. Keep in mind that those can be tested. We can ask you questions about things that we did in the security exercises. So to scan a network, ping is for a specific host if we're looking to contact it. So that's not it. Traceroute is going to tell us what the hops are to get somewhere. IPconfig is your own address. Route is just going to give you the route that you're getting to get out of the network, any active routes on your particular network. But to scan another network, the command that we would use there is nmap. And that's from security exercise 16, where we were trying to figure out which machine on the network was the evil attacker's computer and which one was the router. So finally, part G, 5 points. We're just matching the terms to the answer. So ability to correlate recorded actions with its originating entity, non-repudiation. This should be you should have these definitions on your equation sheet and be able to match them in case they show up on the exam. Protection of information from unauthorized modification, that's integrity is modification. Reliable access to information by authorized users, that's availability. Protection of information from unauthorized disclosure is confidentiality. And finally, ability to verify the identity of an individual. We only have one left, and that's authentication. Okay, so that's question 2.